So
So the title is changed.
yes, of course. So we are very happy to have Yoel Groman from Einstein Institute of Mathematics. He is going to talk about almost toric fibration on K3 surfaces.
Thanks. Thanks for inviting me to this talk. I'm actually very happy to be here. I've already told you about this bait and switch. So basically, the summer, like the conference had like these two themes. One of them was SYZ fibrations, and the other is kind of using SYZ for proving mirror symmetry. So I had what to say about both of them, but kind of in my view, somehow the thing which still somehow I feel like the Floer theory part, the mirror symmetry part, will follow once we have the SYZ fibration. Like the SYZ fibration part is the one that's the current bottleneck, in my opinion. So basically this project, it's joint with Pranav Chakravarti, and we started it in order to solve the same kind of problem that Ilya said, that he has this 80% theorem. And what I can say is that we failed, but I think we came up with a nice result, nevertheless, for its dimension. So so let's what is the setup? Okay, so we have a Calabi-Yau, Calabi-Yau twofold, K3. This is a K3 surface. Okay, so we will consider something called the Kulikov model. So the setup will be as follows. So we have a family X over a disk with X as a fiber. Let's call this map phi, and we assume a number of assumptions. So first, of course, we have a smooth total space. Two is that we have a global Calabi-Yau form on this total space, which restricts omega, which restricts to omega, and okay. So whenever you have, and we're of course assuming that there's some central fiber x0, and this central fiber, whenever you can associate with it a dual intersection complex, and the assumption is that delta, which is the dual intersection complex, of kind of the central fiber is two-dimensional. And when you have this setup, this is called the Kulikov model of type 3. We have these three things. Or also a maximal degeneration.
And the minimality comes in the second condition.
Like the fact that this kind of dual intersection complex is two-dimensional.
Yeah, but you could create by blowing up much more, so the second two.
Yes. And in this case,
and
yes,
just scalar or is project?
just Kev.
So it is scalar.
It is. Sorry, I did not yet say anything about this inflection flow. Sorry, not yet say. Did not yet say. Okay, so there's going to be 4 and 5. Okay, so in this case, delta is kind of a sphere. Okay, and then I'm adding. So these are just these are assumptions. So now I'm adding symplectic geometry assumptions. So 4 is that we have kind of a symplectic form. On the total space, and okay, so maybe I'll say kind of a technical assumption.
So this is not the quartic, right? The quartic does not fit.
The quartic.
It does
Well, what I mean the toric degeneration of the quartic.
blow up the divisors and you get this.
So the quartic fits into this after some adjustments. I guess that's what he's saying, and that's what. So if you take the toric degeneration of the quartic, it does not fit into this. Like the one that you're.
But you can blow up.
Yeah, and I will actually talk about it, like how you relate. Yeah. So basically, this will be a central. I mean, hopefully, this will be a central part of the talk, kind of relating the case of toric degeneration. Okay, then there's a technical assumption. I don't know if it needs to be said or not. Okay. So 4 is that. So x0. So I will write x0 as, and this is a central fiber. I will write it as a union of components, and then xij is just my notation for intersection, and xijk is triple intersection. Okay. Now, okay, so for omega symplectic form, so we assume that somehow that some kind of orthogonality. So you have these you have these intersections. So these intersections are basically spheres which live inside the total space, and then we require that these spheres meet orthogonally, symplectically orthogonal. Maybe this is a redundant. Maybe it can. Okay, and then
Symplectically or metrically?
symplectically. Symplectically. Yeah.
So you keep them, did you perturb them, or are they complex?
What do you mean? So this is just an assumption about how this. So there's a symplectic
They're
form, and I'm
complex
saying
submanifolds.
what?
They're complex submanifolds.
So yeah, this is so yeah. When I say K3 surface, I mean kind of something which is holomorphic. I start with something holomorphic, and then I'm saying there's a symplectic form. Like 1, 2, 3 is a holomorphic thing, and then there's a symplectic form.
I think it's not so easy to make things perpendicular. But in symplectic category, it's very easy. So that's why I keep asking.
Yeah. So I'm assuming
But the
symplectic form.
xij are complex. No?
What?
The xij are
Yes,
complex.
yes.
But the form is not scalar, you're not assuming.
The form is form times or okay, omega times
That is not compatible.
j. The only thing I need is for omega to tangent j. But I think even if omega is compatible, I think you could perturb. Let's just make this assumption. Let's just make this assumption. And,
So let's reiterate this because I got lost.
Yes.
You have these components.
yes.
You cannot have color form holomorphic submanifolds which are also symplectically orthogonal. This would be just too much. So here, what's relaxing is this condition that omega is not necessarily of type 1, right? It's you deform omega.
Mm-hmm.
So let's consider the example. You have 2 divisors which are complex, but they meet, like the angle between them is 30 degrees. They are not orthogonal.
Mm-hmm.
So now what you do, you deform symplectic form so that they become orthogonal.
Yeah. By the way, I think you can make it compatible and flat. Like you can modify the symplectic form so that it becomes flat in the neighborhood of flat. I think you can do it even with compatible, but yeah, time is good in time. Um, so, okay, so yeah, so we need this orthogonality somewhere. I actually don't remember where I'm using the orthogonality right now. Hopefully come up. Yes, okay, and then we're making an assumption. Okay, so this is 5 and 6, maybe a redundant assumption, maybe not. So
achieved by this theory of regularization that was quoted by Varolgunes.
Yeah, that's how we do this. Okay.
yeah, this is anyhow. Okay, so I'm assuming that each component xi carries an almost toric fibration with kind of, or maybe let me say, an almost toric fibration with like x with mu over j as kind of a boundary. So the assumption that you're an almost like that you have this setup where you have this Kulikov model. It means that if you look at some component xi, then it's then the spheres here xij, xi1, xi2. Okay, they form a cycle, and this like xi with this union is a Law-Calabi-Yau pair. So the assumption is that there exists on this component xi, there exists an almost toric fibration. That's mu I and xi to b. And what this means is like b basically looks exactly like this, and it has some. So an almost toric fibration means you have a bunch of like you have a Lagrangian torus fibration, which on the boundary it looks like toric variety, and at these points it's like it's a nodal point. So this is called a focus point. It means the fiber over it is a pinch torus, and you have some kind of monodrome, particular monodrome on the border. Is that? Okay, so this is our assumption. So now, okay. So now let me get somewhere. So this is the setup we're working in. Now, so first let's make an observation. So in this setup, we can define an intersection complex. Okay, so the intersection complex is kind of the vertices are kind of points xi, j, k, and then you have edges with xij, because this setup, basically the setup tells you that they all kind of they arrange into cycles. That the xi, like the boundary divisors, they arrange into cycles. So in particular, like each xij is a sphere, and it intersects. It meets exactly two of these vertices, and then you have two cells, or the xi's. And so this is something you can define when you have this Kulikov model, and this gives us the mu i's, they induce a piecewise affine structure on the intersection complex. Okay? So they piece together to give a piece. Sorry, not a piece. A piecewise nodal integral affine. So what do I mean by this? I mean that you have all these pieces, they glue together, and then in the interiors you have just a nodal integral affine structure, and then you have kind of, it's piecewise because you have this one skeleton. Okay, so this one skeleton is where you have where you don't have an integral affine structure a priori.
What does nodal?
Okay, so nodal means exactly this: that you have some points which are more so a nodal singularity of an integral affine structure means that you have something which is locally modeled on, like it's not defined at this point, and the monodromy around it is given by kind of 1, 1, 1, 0. That's right. Okay, so we have this. Okay, and then 3 is that this actually extends. Okay, so 3 is more than an observation. It's a little. 3 is kind of a claim. So there exists a canonical extension. It's more than an observation, I think. So there exists a canonical extension to a nodal integral affine structure. So or maybe I should say unique, or which is characterized by so near a vertex. So you should think that near a vertex. So you have this one, and then you have the next one, which is next to it. So like a corner, you could think of as, you could always identify it as the corner in kind of, you look at the like you can always identify such a corner piecewise by piecewise affine map with the boundary of kind of the quadrant, such that kind of these faces match and kind of are integral, like on this restriction to each of the components is integral affine. So on this corner there is kind of a particular integral affine structure, which is given by the projection. You take R3 and you mod out by the sum E1 plus E2 plus E3. Okay, so this projection, so this gives you a projection from the corner to some copy of R2. That defines, so this defines some kind of extension of the piecewise affine structure to a neighborhood. And the observation is that when you do this, it extends globally, meaning that you don't have any singularity. Since you have no singularities on the edges, there's no monodromy, and this gives you kind of a global integral affine structure with nodes. Okay? So this is some kind of observation, and the reason for using this kind of, like, why is this true? So notice that this is the thing. Like, if you think in terms of symplectic geometry, these integral affine structures, they correspond to torus actions. And this corresponds exactly to looking at something which preserves value. Like, this generates kind of the thing which doesn't, like, there's some duality here. So like this is kind of the place where the torus, this is where the moment map for the volume preserving torus lives. Okay? So And so somehow the fact that you have a global Calabi-Yau form tells you that it's exact. It's some, maybe, yes.
Can I ask?
Yes.
The fact that it says S2 is like the sphere, is it an assumption or it's?
The fact that it's, okay, so, no, it's not an assumption. It's not an assumption. So this is kind of a theorem by Kulikov and Pinkham.
So this is also a sphere.
This is also a sphere, yes. So, okay, so now finally I can state the theorem.
But you also, what happens on the edges? You don't say anything about what happens on the edge.
Again, like what happens in what context? Like how the integral affine structure? Or?
Yes.
So I'm saying, like these edges, they do have a length, right? They are kind of straight.
You didn't say that, did you?
I didn't say it.
So there is still an integral affine, like one-dimensional.
Yes, like it's a piecewise affine structure which has kind of, there is something here.
So from the interior, it restricts to the to the linear.
Yeah. The only thing that you don't have is kind of when you go kind of in this direction, you don't know how to continue. That's a priori.
It's
But-
torus, the fiber, it's
The fiber is okay. So the fiber is an S1. That's what like when you have an almost like fibration. So the way it works is kind of for the interior you have a torus.
But I think the question is very clear. We explained it at the vertices. What is it on the edges? You didn't say.
Like what is the integral affine structure?
Yes.
So I'm saying.
Or maybe we can just finish. There is a canonical extension to integral affine structure on what?
Okay. So there's on the entirety, which is uniquely kind of characterized by this. That this is what happens near the vertices. And I explained the reason. So what's going on is you have an integral affine structure in this side, on this side, and then you have on neighborhoods of vertices. And the fact that you have like there's a claim here. I'm not saying there's a claim. It says that when you do this, there will be no monodromy, and that will give you an extension of the integral affine structure.
Because all the angles like 120 degrees, so this is very low.
It's like it's basically you can use this to like.
Okay, okay.
You can use one side
I think
to
he's
define
saying
this.
something more. He's saying, for example, if he didn't have a holomorphic volume form, he wouldn't have this.
Right.
I understand.
If you take a cube, right?
That's precisely the statement. So
Yeah.
that's the all the angles are the same. Like all the angles are 120 degrees.
Yeah,
That's-
could
that's
be.
the
Yeah,
statement.
that's probably one way of saying it. But I'm saying this is a claim. So like shouldn't have called it an observation. I should call it a lemma. This lemma. I'm not going to discuss the proof. I can try to hand wave like why it's true. It's a lemma, and yeah, I'm not saying it's obvious, but okay. So now theorem. So I'm saying that okay. So the generic fiber carries an almost toric fibration over this delta star. I wanted to give it a canonical extension A. Okay, let's give it a name. Okay, so over this. Okay, so you have this geometric method of defining, like there is some way of constructing, a fairly explicit way of constructing an integral affine structure on the sphere, and I'm saying that the generic fiber carries an almost toric fibration with this base.
And almost toric is in this, again, this is.
Yeah, so almost toric fibration means that you, so it means that over, so in this case there's no boundary, because you have a global integral affine structure. It means on regular points you have a torus, and at nodal points you have a focus.
That's what you call by almost toric.
Yeah, that's an almost toric fibration. Yeah, so it's kind of that two-dimensional no integral affine structure with very simple singularity. It's the same. Okay, so so what I'll do, let me kind of first prove this, I give you a sketch of the proof, and then I'll try to relate to the case of, like, there's a different different thing which you can do, which, as Ilya asked, like you start with, say, a hypersurface in some toric funnel, and you degenerate it, and that does not fit into here. And that thing also, there's some integral affine, some nodal integral affine structure, and how do these things relate? And surprising, or yeah, also, and we'll talk about it. Okay, so first let me just talk about proving this. So,
But before,
yes.
how unique is that?
How unique? Okay, so
Can you actually recover? Like,
so how given okay, so given these ATFs, this, like, there's a procedure, like given this these ATFs, you on the X on, sorry, where is the assumption? Yeah, like so given these ATFs, that determines, that gives you A. Unique up to, like, the procedure kind of gives you something up to Hamiltonianized with this particular integral affine structure. But note that this thing is not unique because you can apply many changes.
wow, I mean, you apparently cannot move arbitrarily this points, right?
These points cannot be moved arbitrarily, but they can't, like, each of these points has a monodromy invariant direction, and you can move, you can slide. There are operations which are called nodal slides. So at least nodal slides are you can do. But those are operations, like, if I give you this, you can apply those operations to this. Like, whenever you have an ATF and you have nodes, then you can move them around freely in the monodromy invariant direction.
So you're saying that once you have this structure on this central fiber,
yeah,
then there is a canonical procedure.
Yeah. Yes. Exactly. Yes.
Construct a vibration.
Procedure is canonical up to Hamiltonian isotope, which means you might be changing the map. Like the Hamiltonian isotope, you can change the map from the general fiber to the base, but the base will be the same.
In this whole story, there is a fixed big omega and a fixed small omega. So what is the relation of the fibers with this data? Are they special?
So the fibers.
Are they Lagrangian?
Yeah. So and also fibration means a Lagrangian torus fibration, and they have Maslov 0 with respect to this. Okay, so now let's see how you prove it. Okay, so there's a few steps here. So first there's some kind of easy thing. Okay, so the mu I, which are a priori, they're defined kind of in each xi separately, they glue to kind of a map mu. So you have the union, like you have a map from the central fiber to the base, which you can identify with the union with the base B, which is kind of the base B is. And I'm identifying it with the intersection complex. So there's a way of gluing together the intersection complex from these BIs, and then there's a way of gluing together, well, these Xi's are given, but you can kind of modify. So after you just have a bunch of maps from UI from Xi to BI, you can glue them together to give a map from the union. Okay? This is a map on the central fiber. Okay? So and then fix a path.
I got a question.
Yes.
So what happened close to the boundary of the Xi? Do you do the Nakayama construction to create toric? Because so
No. So this is kind of a singular thing. So the union of xi is not, it's kind of, it's just a
So
normal,
it is the union of xi, and then some fibers will be lower dimension.
some fibers are lower dimensional. So this is not an right, exactly. So that's the, so this, yeah, there's no, we're not blowing anything up. We're not like this, so this is kind of a singular thing, and it has a map. And then, okay, so given a path gamma in kind of the epsilon. Okay? So given a path the epsilon, this gives a map from P gamma to x0. X0 is the same as this union. Okay? So you have a map which is parallel transport. So usually parallel transport you go it's well defined through regular fibers, but you can show that the parallel transport is defined and continuous even if you flow up to if you go all the way to the singular fiber. So it's continuous. Okay, so I'll have to erase. Maybe let me just before I start erase the things. Okay, so this means that we have a map mu composed with P gamma from some regular fiber to this base. Okay, so we have a continuous map. So I'm claiming that this is continuous. And now the question is, what can I say about this map? So I can say that for points which flow, so for points so we get a continuous map. So let me draw the base over here. So we have some kind of one skeleton. So I have some one skeleton, and then there are for points which flow into the interior. I get it's a smooth map. For preimage, okay, smooth on. So smooth on preimage of the complement of the one skeleton. Okay, and so there I have, and this means that points which go to the interior, so either they're a Lagrangian torus fiber, or when they go to a node, they give me a nodal torus. And the question is, what do we do about points that flow, that kind of the parallel transport takes them into these singular, into this one skeleton. So this leads me to the second step. Okay, are there any questions? Anything unclear? People are kind of, it looks like to me like people are staring, so am I saying, is there something? Like it's fine. Fine? Okay, good. Okay, so the next step so the next step is the following. So step 2. Okay, so pi can be modified in a small neighborhood of these triple points. For each of these triple points. Okay, so I just erased it. So pi is kind of pi is the thing that defines the let me write it again. So pi is the map which goes from the general, so from this family to the disk, whose fiber gives me this fiber. Okay, so this is my symplectic fibration. And I'm saying I can modify pi in a small neighborhood of so xijk, there are points in this, like there are triple points. So we can modify it in a small neighborhood so that this map, what did we say, mu equals with p gamma is smooth for points mapping near okay. So I'm saying I can add so I can extend like my map after I make some kind of modification. It's actually smooth also for points which flow into a small neighborhood of the verse. Okay. And the reason why this is true, so this is something which I don't know. Some people attribute this to Rouen. I didn't see. So the idea is like this. So locally, when you look at so pi is something which defines a normal process divisor. So locally, it looks like first order pi. It looks like zi times zj. So it's like this map, and this one is kind of like you can locally model. So this is this plus higher order terms. Now you can locally model. So now,
Higher order.
what?
The higher order.
A little off. Maybe okay.
Just write higher order terms.
What? The higher order terms.
Hot.
Yeah, plus high. Okay. So now you have a very nice model for something like this. Like if you look at C3 in the neighborhood of 0, and you have this map Z1, Z2, Z3 to C, then this thing carries a torus action. So locally you can model, like you have a map, a mu, to R2, which you can think of as this thing I wrote before. Which I'll just write it in coordinates. It's given by Z1. This is given by it has two components. Okay, I think I want to write like this. So never mind the formula. Okay, this generates like this in symplectic geometry. This generates a torus action, which preserves this map. Right, the product of all coordinates are preserved by something which, because this rotates z1 in one direction and z3 in the opposite direction. This rotates z2 in one direction and z3 in the opposite direction. Okay, so and you can think of so what you want is you so if you forget about holomorphicity, okay? If you forget about this map phi, and you just look at the torus action, then you have some kind of Darboux neighborhood theorem which tells you that this is that somehow when which tells you that you can describe, or let me say it differently. So this let me say it differently. So look in a neighborhood of xijk. So you have this collection of divisors which each have torus actions. You can extend that torus action to a neighborhood of xijk. So you have a torus action with some neighborhood of xijk, and symplectically it's indistinguishable from this setup. Where you have this torus action, and infinitesimally like then you have this additional item, which is this map. At least to first order, it looks like this map. Now, if this were precisely, if there were no higher order terms, then the point is that the moment map mu doesn't change when you move along, when you have an equivariant, like when you have a symplectic fibration, which is invariant, then the moment map doesn't change, which means that under this parallel transport. So this means that you don't have to flow all the way to the singular point. You can stop a little before, and therefore it's smooth. Okay? So that's what would happen if you don't have any higher order terms. So, but the problem is you do have a higher order term. But here there's something which there's Donaldson's lemma, which was a number of people mentioned it here. So there's this relation between symplectic and holomorphic geometry. So you can, like you know that if something is if you have a holomorphic map, then it has symplectic fibers. But it's also true if you have an almost holomorphic map. You still have symplectic fibers if you are careful in how you perturb your map. So the fact that you have this kind of plus higher order terms means that in a small neighborhood you can so let's write this. So in a small neighborhood you can interpolate. Okay. So let's call this pi 0. Okay, so this justifies the second step, and now we come to the really okay. So this means, well, if you believe me so far, we've extended the integral affine structure, and now what's missing is not integral. We've extended, like we made our map. We have a Lagrangian torus fibration. We have a map. We know that it's a Lagrangian torus fibration, except on interiors of edges. That's what we're missing.
That's the interesting part.
What? Yeah, that's the interesting part. And okay, and we spent like a very long time thinking that the same kind of trick that you have here should be possible to do also for a neighborhood of P1, because it looks so like, because these neighborhoods of P1, they also have some natural local infinitesimal local model. You have these, they look like toric Calabi-Yaus. These toric Calabi-Yaus also come with some kind of function, so some kind of global function. So right, O minus 1 plus O minus 1 over P1. If you know a little bit about it, it has an equivariant function. So it looks like it should work. And we spent a great amount of time, and I don't know, it just kind of. So I can't say for sure like that. Like I would like to also say a negative result that it doesn't work, but I don't know if it doesn't work. But we tried, and like it just every time we thought we had an 80% theorem, there came we revisited it and we found that no, it doesn't. Something still isn't right.
Hey, can I just like get a very quick? Why wouldn't this follow from your result? I just when I saw your result,
What you say it
this theorem that he's trying to prove, that theorem. So
I think we could prove
Which theorem?
this theorem,
Ah,
there's
that-
one
that-
theorem on the board.
Okay, you think you
that
prove it
is
with
alternative technique. Different ways
But-
of approaching. But,
For
but-
example,
but-
it would mean that
no,
it's
but-
not wrong.
But our base wouldn't be the dual complex, but the expanded. So
but you would have an almost toric fibration on the
yeah,
oh,
because
because
so it's not exactly the dual.
Yeah, so we are missing these hexagons, right? So this
the interior.
But he's given the
No.
hexagons.
The
He's
hexagons-
starting with the hexagons.
Because the hexagons are given in the data.
yes, so we need to
You need to interpolate the torus
They
fibration.
give
So
them
this
to us.
is
yes, I mean we
This is
check
what we have.
Yeah, but I mean, you know,
There
this
is
is
a
like,
lemma to
this is
prove,
the
right?
holes in your.
Yeah.
Yeah, so we have like our holes.
Like you just filled them with.
If they give us the holes as a datum,
Yeah.
I think we would.
No, you have to be able to interpolate.
Yeah,
Yeah,
we
we should
look
let
at
him
them,
tell you,
but
but
it
can you,
matches,
can you,
right?
Yes.
see, like, to
Okay.
me it sounds like it follows, but he says it doesn't follow. Can you also think about this and see?
I'm not saying it doesn't follow. I think it's not like interpolate. Like I don't know the details of where your toric come from, but interpolating two torus fibrations, you have like two separate torics which come from
My
different
feeling
sources.
is that from the same data, we could reach very similar result, but using the expanded dual complex and fill with the exons. This is my feeling.
Okay,
But details,
but yeah.
yes,
so-
of course, haven't been checked.
So, like, there's kind of things with symplectic topology. Sometimes like something looks easy and it is easy, and sometimes something looks easy and it's just not. And yeah, so I'm not making a claim in any direction. But yeah, but how do like yeah? So filling the holes. So how do we fill these holes? So here we use some hard symplectic topology. So this is where like we gave up, like we couldn't make it. So this is where we have to apply some methods which work only in four-dimensional, only in dimension 4. And what goes on here is, well, you look at the pre-image of a rectangle like here, then you don't know what the map, like you have a continuous map, you don't know what it looks like over some interval in the interior, but you understand completely well what it does to the boundary. And so using like a bunch of results about hard symplectic topology, you can show that this is actually okay. So let me just say, I don't have time for the details, but I will just say, using some hard symplectic topology. So I call this. Let me give this call this R. Hard symplectic topology. And when I say hard symplectic topology, it doesn't mean that we worked hard. It means that somebody else. No, it means that it's like it uses geomorphic curve theory. That's okay. That the pre-image mu. So the pre-image is symplectomorphic to R cross T2 in kind of in a fibration compatible way.
Okay, I can make a new remark.
Yes.
Okay, and I actually use something similar to this to build our tropical Lagrangian.
Mm-hmm.
So not exactly this situation, not exactly the same, but we also use we cannot determine exactly something near those regions, and then we expect we have even have a singularity inside. So then we build a symplectic fibration, and then we use four-dimensional symplectic topology and the classification on the boundary. There's a unique filling of the standard contact free ball.
Yeah.
And then to extend the tropical Lagrangian to the end.
Yeah. So actually, yeah. So by the way, yeah, we also one of the things ingredients here is your thesis about kind of. It's not to prove this, we need to somehow compactify, and then we have to move some divisor, some kind of show that kind of like we first get a result. This is diffeomorphic to R equals T2, but then to get that this is symplectomorphic, we need we kind of maybe there's another way. So we do some kind of we turn this into an S2 plus S2 and use some kind of Gromov theorem. But then this Gromov theorem moves the divisors, and then we need to move them back in order to get this statement about R cross T. Okay, so this uses some. Okay, so that's the sketch of the proof of this. And yeah, I'd be happy if you claim or if you think. Anyhow, we're going to upload this. I'm going to say, I mean, it's just another proof.
We don't claim.
Yeah. Okay, so this is this is this theorem. Now the question is, how do you relate this? So there is what happens when you have like how do we relate this to the case where you have a smooth toric file? Okay. So let's look at the case. Let's just consider a case. Let us consider just the case of the quartic. So consider x is just the zeros of x is just the quartic. Let me just consider like you have a space E, which is the set of x, y, z, t in, let's say, P3 cross C, is such that
You might need one more variable. Or x is maybe x1, x2.
yeah, you're right.
Double.
X1, X2, X4, and T. Okay, the homogeneous coordinates. Satisfying the homogeneous equation, x1, x2, x3, x4, plus t minus x1 to the power of 4, plus x2. Okay, so let's just think of this example, okay? Equals 0. And I never remember if I want to put the t, on which side do I want to put it?
It depends on you want to 0 what we.
Okay, so this thing has a map to C, which just takes a point and maps it. Okay, it maps it to the value of t.
I think you want to put it on that.
What?
You want to put t
No,
on
we still don't know what he wants.
Okay, so it equals 0. Yes, you're right. No, that's exactly. Okay, so the question is, okay, so this is not a Kulikov model. So okay, so E has the total space of E has double point singularities. Okay, now these these double point singularities. Let's draw a picture. So basically you have some kind of, okay, so locally it looks like this. You have, let's say we're looking at, so you have, okay, it has double point singularities where at points, let's call this S0 and this S1. So at points where S0 equals S1 equals T equals 0. So each such point is a singularity of the total space. And the picture you locally have, so let's say we're looking at Z1, Z2 equals 0. And here you have, okay, and here you have Z1, S1 equals 0, Z2, S1. Okay. So you have, okay, so this is a picture of a singularity. You have like four things meeting. Now this singularity in the complex world, it can be resolved. So there's a local model for resolving it, and the drawing so you resolve it by, let me draw another drawing. So this can be resolved by something called a small resolution. So small resolution means, okay, let me draw a picture. So you can kind of replace this by the local model for like O minus 1 plus O minus 1 over P1 can be kind of glued in. And the way this picture kind of relates to this picture is that you have, so if let's call this V1, V2, and this is, I don't know, let's not do it. Okay, so we have some blow up here. So this is kind of the exception, proper transform. And proper transform. Okay, and this is, and we introduce kind of an exceptional locus. And notice from the point of view of the total, like we've made a choice here. Like we've made one, we made this choice. We could do the other blow. Now in simplicity, so if all you want is to construct a complex manifold with no singularities, you just make whatever choice you want, and you're done. But in the symplectic category, this doesn't work. You can't just blow up. So there's a criterion. There's a criterion for doing this. So maybe you're kind of familiar with blow up. So in symplectic topology, you can blow up. So this is called small blow. I'm trying to explain what's the problem. So there is blow up in symplectic topology where you replace a lower dimensional thing with a divisor, with a hypersurface. But if you want to replace something which is of dimension 0 with something of dimension 1, and you're doing it in a 3-dimensional manifold, this is not kind of a symplectic surgery. This is not something you can achieve by doing some surgery. So actually, like there's a claim by. Okay. So there's kind of Smith, Thomas, Yao, which says that let's call E tilde the blown up space. So E tilde has a symplectic structure. If and only if we can find a real kind of a real cycle such that sigma intersects E positive for all exceptional spheres. Okay, and if you have such a cycle, then you just take so you have like E tilde to E. I don't know what. Let's just give a name Q. P. P. And the symplectic form is P. Like you pull back omega, and you add a very small multiple. A very small multiple of kind of the Poincare dual, or let me say as the classes. The classes is a very small multiple. Okay, that's okay. So I don't have time to explain that theorem, but I just want to point out something. So in this.